Hey, welcome back to our very last segment of the very last lecture of Functional Programming 101. And in this last segment, I'm going to make up for some clowny code that we wrote a couple of lectures ago. I don't know if you remember, but when we were talking about list comprehensions, we wrote a really embarrassing version of a prime number generator. And we want to do better. I mean, that code was not the most beautiful code I've written in my life. So let's redeem ourselves and write a beautiful way to generate primes that leverages lazy evaluation. So here's a recipe to generate an infinite list of primes in a very nice way. So we start that with the list of all natural numbers starting at 2. And then we look in this list and we mark the first value in that list as a prime. So the first prime here is 2. The next thing we do is we say, okay, if we know that this thing is a prime, then all multiples of that number are not primes, right? So for example, 4 is a multiple of 2, so we know that 4 is not a prime number. So given that the first marked prime, we're going to filter out all the multiples of that number from the list, and then we just, we know that then the next value is the prime, and then we delete all the duplicates, and so on. Now, this algorithm is really old. This algorithm was really invented before any of us was born. And this is called the sieve of Eratosthenes. Okay, so this was invented by ancient Greek mathematicians. Let's draw the picture here of a few of these steps. So we start here with the list of natural numbers starting at 2. First number here is a prime. So we cross out all the multiples of 2. So we cross out 4, 6, 8, 10, 12, etc. And now the first number that's not crossed out, 3, is a prime. So that's a prime. 4 was already crossed out. 5 is not a multiple of 3. 6 is a multiple of 3, was already crossed out. 9 was not crossed out yet, is a multiple of 3, so we cross that out. And we continue. So now 5 is the next prime. We're going to remove all multiples of 5, etc. So here you see that fairly easily we find the first few prime numbers, 2, 3, 5, 7, and 11. Let's translate this into Haskell. All right? And the beauty of this is that this algorithm is more or less directly translated into Haskell. Now, of course, there's a huge field of literature on different versions of this sieve and more efficient versions. You can spend years researching that. It's a beautiful area. But this is the simplest version of this, and to show you the power of lazy evaluation and infinite lists. So we start here with the infinite list of natural numbers starting at 2, and then we're going to sieve out all these numbers, just following that recipe. So how does a sieve work? Well, we start with the first number in the list, that's a prime. And what we do is we return that number, and then we say, throw out all the multiples of p from x's, and then recursively go back to step 2, sieve out all the numbers from there. Isn't that beautiful? I mean, here's a quite imperative description. We return to step 2. But what we see here is that return to step 2 is really this recursive call here. All right, so we start with the numbers from 2 and up. the first number must be prime. We remove all the numbers that are duplicate, and then we just sift the result. That must now start with the next prime. We're going to kind of put that on, keep that, and then sift out the rest, etc. Now you can also see why there are more efficient versions, and we already saw that here, because multiples of 2 are eliminated, and here multiples of 2 are eliminated. And so, there's many ways you can do this sieve, in a more efficient way with kind of wheels and whatever. Again, I would just Google for sieve of Eratosthenes, and you will find a large collection of papers that describe different variants of this that are much more efficient and that use all kind of properties of natural numbers to make this computation more efficient. Okay, but if we execute this, primes, this thing will just spew out an infinite list of prime numbers. It will just continue, and after a while it will get slower and slower because, the prime numbers, there will be more space between them. But, you can just run it forever, and if you have enough patience, you will find the prime number that you're looking for. Now, again, since this is an infinite list, it's not really an infinite list because it's a recipe for generating an infinite list. So if we only take the first 10 prime numbers, this function will terminate and just give us the first 10 prime numbers. It won't first compute all prime numbers. No, it will just do enough work to give you the first 10 prime numbers. Or if we want to take the prime numbers that are less than 15, we can use take while, and again, just enough work will be done to do that. Now, imagine that you're in an imperative language, or in a strict language. Now you have to choose whether you want to take the first primes or you want to take primes up to a certain number, because you cannot do this in this modular way. So you cannot first compute the primes or have a promise to compute the primes and then take the first 10, and then use that very same description of computing primes and then take all the ones that are less than 15. You have to immediately fuse, let me see if I can, yeah, it's too hard to not stand in front, but you want to fuse take 10 with primes into one function and take while less than a certain value with primes to get one function if you don't have lazy evaluation. And a very nice paper to read here is John Yu's paper, Why Functional Programming Matters, that has many more examples of this, the fact that lazy evaluation makes your code more modular. Okay, that was the end of the lecture series. I enjoyed it enormously. I hope you did so too. And please try to use everything you learned here to become a better programmer. And I'm pretty sure that is the case. And I hope to see you in another MOOC at another time. Thank you so much. And again, see you soon. Bye-bye.